Hello friends. In today's lecture, we will actually be looking at two very classical models of the turbulent boundary layer, which will actually simplify the algebra substantially, but it does so because it involves substantially more approximations than what we did in the previous class. In the previous class, we actually used an approximate boundary layer profile in the form of a 1/7 law boundary layer profile, and integrated that over the boundary layer to get the expression for shear stress and the Prandtl number. In this class, we will basically go back to Prandtl and von Karman, the way they visualize the turbulent boundary layer, and understand in simpler terms. So basically these two models will be rather more approximate than the integral method. The integral method itself, we know, is an approximate method for getting the expressions. So the expression of wall shear stress and the Prandtl number that we got in the previous class, that is the skin section coefficient and Prandtl number that we got in the previous class, were themselves approximations of the more accurate numbers which normally have been obtained through experimentation. These two methods will provide even more approximate results, but the importance of these two methods is basically the classical flavor. So when boundary layers were first understood, the turbulent boundary layers were first understood, how did the great workers of fluid mechanics like Prandtl and von Karman conceive them? So we'll, as we go on, point out what are those approximations which eventually need to be relaxed. But then what we will also get is a very simple and elegant solution that comes out without too much of mathematical complexity, and we'll be able to compare that with the integral method result that we got in the last class to get a feel. So in today's class we'll understand the two-layer model of Prandtl and the three-layer model of von Karman, and from there in the next class, I think most likely I'll be able to wind up the discussion on turbulent boundary layer. We'll summarize how to go about using these results in real problems of convective heat transfer. So let's start by going to the whiteboard of the Prandtl's two-layer model. Yes. So basically what did Prandtl conceive the boundary layer as? He conceived the boundary layer as composed of two regions. One is the sublayer and the other is the turbulent core. Okay. So sublayer is a region where molecular mechanisms dominate. So nu is much greater than nu t and alpha is much greater than alpha t, so much so that the turbulent quantities can be neglected. And what else is important about the sublayer? U, V can be neglected. Okay. So with these approximations, and we can also say that in the sublayer the velocity and temperature profiles are linear. That can come from this one. So if u and v can be neglected, then you get from the boundary layer equation, which is u del t by del x plus v del t by del y is equal to alpha plus alpha t into del square t by del y square. And now since u and v are both negligible, this becomes equal to 0. So what happens is the del square t by del y square multiplied by alpha plus alpha t goes to 0. So if I say that if I write this in the form of since alpha t can vary with y, I should write it in slightly different form. So let me write this as del by del y of alpha plus alpha t del t by del y equal to 0. So then since this is 0, you get alpha plus alpha t into del t by del y is approximately a constant with y, and therefore this can be equated to q dot wall divided by rho Cp. Okay, because and with a negative sign, of course, because q dot wall is minus k del t by del y at y equal to 0, and therefore if I divide both by rho Cp, I get this as alpha, and at the wall, of course, alpha t is negligible, so this is so this expression, when alpha t near the wall, very close to the wall, goes to 0, this is alpha is k by rho Cp, and the negative sign comes here. So this is your expression for boundary layer, and since this is a constant, the slope del t by del y with respect to the slope of temperature with respect to y is a constant, so the temperature can be taken to be a straight line from T wall to some temperature called TSL, which is the temperature at the edge of the sublayer. The same thing can also be done with velocity, because your momentum equation also looks similar. So you will get nu plus nu t into del u by del y is equal to tau wall by rho. This is the constant. This is also a constant. You will get, because del by del y of nu plus nu t del t by del u by del y becomes 0 because u and v are very small. Then this gives me del u by del y is a constant in the boundary layer, and therefore that will also look like something like this. This is u is equal to 0 at the wall, and let's call this as USL. So this actually you can say del t by del y in the sublayer would be equal to TSL minus T wall divided by delta SL, where delta SL is the thickness of the sublayer. So you can see one approximation already here, that we are assuming that the sublayer for both velocity and temperature is the same. Okay, so this is one of the approximations that is involved in the Prandtl sublayer model, Prandtl two-layer model. He did not try to substantially distinguish the thicknesses of the thermal sublayer or the conduction sublayer and the momentum sublayer, that is the viscous sublayer. So you look at the simple single sublayer, and inside this sublayer you say both of these quantities, the molecular quantities, dominate over the turbulent counterparts, and therefore the del t by del y can be written like this, and similarly del u by del y can be written as USL minus 0 divided by delta SL. So if I divide these two equations one by the other, I'll basically get q dot double prime, this rho would get cancelled, divided by tau wall Cp, and that will be you'll get a ratio of these two, and you'll get a ratio of these two. So if I cancel out the y there, because these are written at every location, so if I then this basically become a minus dt by du. Okay, so so suppose I call this as equation A and equation B. A by B is what we do. So let's do that on the next slide. So what we get is dt by du with a negative sign is equal to dt by du is equal to q dot double prime wall divided by tau wall Cp. Okay, and actually there is this ratio of alpha plus alpha t divided by mu plus mu t. Okay, and what we presume in this region is that you neglect alpha t and nu t, so this is negligible and this is negligible in the sublayer, so you get an alpha by nu, which is 1 by PR, and that can also be written here, or we can simply write this as equal to minus k times TSL minus T wall divided by mu times USL minus 0. Right, the delta SL would get cancelled between these two, so this would simply be minus k by mu multiplied by T wall minus TSL divided by USL. Okay, so this equation is called the equation of the sublayer, so I'll write it separately again. Q dot double prime wall divided by tau wall Cp is equal to minus k by mu multiplied by T wall minus TSL divided by USL. Okay, or okay, so the minus sign has been absorbed, that's why it's T wall minus TSL, so this minus sign is gone. Okay. Okay, so this equation is called the equation of the sublayer. Okay, we call this as equation 1, and this is the equation for sublayer. Okay, now the same thing we'll try to do for the turbulent core. So in the turbulent core, what we do is we don't start with the governing equation, but we just write the expressions for the local heat flux and the local local shear stress. It's not the wall shear stress or the wall heat flux, but it is the local. So local heat flux Q dot double prime at any y would actually be equal to it would be the turbulent diffusivity alpha plus alpha t divided by rho Cp. Sorry. This Q divided by rho Cp would be equal to alpha plus alpha t with a negative sign multiplied by del t by del y at any location. Okay, because this is the equivalent conductivity which will be alpha plus alpha t, so which is k by rho Cp in an equivalent sense. So this q dot by rho Cp would actually be equal to minus alpha plus alpha t into del t by del y. And since it's a turbulent core, alpha is negligible because alpha t is much greater than alpha and nu t is much greater than nu. So this alpha is negligible and this minus would be there. So you can actually write this as q dot double prime at any y divided by rho Cp is equal to negative alpha t times del t by del y. In the same fashion, I can also write for the shear stress. The shear stress will be tau divided by rho. So this is tau at any y. Okay, and this would be equal to nu times or nu t times rather del u by del y. Since the nu is negligible, so if I write this nu plus nu t, then this nu gets cancelled out because nu t is much greater than nu. So this tau by rho would be equal to nu t times del u by del y. And what is assumed is in the core, the nu t is similar to the alpha t in the value. So if you call something called the turbulent Prandtl number, which is nu t by alpha t, is taken to be approximately 1. So if I divide these two equations one by the other, I'll actually get this q dot double prime divided by tau rho at any y. This would be equal to, I can write this as minus dt by du, since this alpha t and nu t would cancel each other. When I divide, suppose this is called equation C and this is called equation D. If I do C by D, I get this. Okay, so this is the expression that I will get. So, and what Prandtl suggested is that throughout the turbulent core, he neglected the changes in this term. So he says this remains approximately constant with y in the core and is approximately equal to q dot double prime wall divided by tau wall rho. So this is the statement that Prandtl made. In some form, it's an approximation. This is not normally going to be true practically with all cases, but in most turbulent flows, when the turbulent flow is a fully established turbulent flow, then this is respected in most cases. So this is the approximation due to Prandtl. Okay, and with this approximation, he was able to say that this is independent of y. Okay, it's constant with y. So that makes us simple. So this is something which then can be integrated between the limits of the turbulent core. So if I take the turbulent core to go from this location YSL to infinity, okay, so I integrate this expression between YSL to infinity. Okay, so I get dt by du is equal to minus q dot double prime wall divided by tau wall rho, and this is integrated from YSL to infinity. Dy is equal to this integral dy from all of this becomes a constant, so YSL to infinity. Okay, so this is the integration that we do. Now what we actually do is we actually separate the variables from the left hand side to the right hand side. So let me not write the integration here, it will come in the next step. So this is the expression that we have. Okay, and so I take the du to this side. Dt is equal to minus q dot double prime wall divided by tau wall rho. into du. Now this I integrate YSL to infinity, and this I integrate from YSL to infinity. So what do I get here? This temperature at YSL is TSL, and this temperature at T infinity is this is T infinity. So it's T infinity minus TSL, and this will be U infinity minus USL, right? So that's an expression that I will get. So let me write it on the next slide. So T infinity minus TSL is equal to minus Q dot wall divided by tau wall rho multiplied by U infinity minus USL. Okay, now I'll take this negative sign this side and write TSL minus T infinity. So TSL minus T infinity is equal to Q dot wall double prime divided by tau wall rho multiplied by U infinity minus USL. Now this is, I'll call it as equation number 2, which is the equation for the core. Okay, now we'll use equation number 1 to eliminate the TSL from here. So equation number 1, what does it say? The equation number 1 says the T wall minus TSL by USL is equal into K by mu is Q wall by tau wall into rho Cp. So I'll write for TSL in terms of that. Okay, so Q dot double prime wall by tau wall rho is equal to K by mu multiplied by T wall minus TSL divided by USL. Okay, now so if I write from here, this mu and K I bring here, and USL I bring to this side. So TSL is equal to T wall minus mu USL by K into Q dot double prime wall by rho tau wall. Okay, so if I substitute that into this expression, then I'll get T wall minus mu USL by K into Q dot double prime wall divided by rho tau wall minus T infinity is equal to, this is the left hand side, and that is equal to the right hand side, which is Q dot double prime wall by tau wall rho into U infinity minus USL. Okay, so I take both of these to the same side, and then I can simplify this. So I'll be able to write Q dot double prime wall divided by tau wall Okay, I've been writing tau wall rho, it has been shown tau wall CP everywhere. Okay, where else did I do that? Yeah, the rho gets cancelled. This will be CP. Yeah, okay. Tau wall CP actually comes equal to T wall minus T infinity divided by PR USL plus U infinity minus USL. So this is something that you can verify by substituting. Okay, it's not a minus sign, it's actually a line category. Okay, so now I can write the expression for Stanton number. Since what is Stanton number? Stanton number at X is nothing but Nu by REPR this would be Q dot, okay, Nu is Hx by K, Hx by K, and Rex is U infinity X by nu, and PR is nu by alpha. So if I substitute this, and this Q wall, okay, this H is Q wall divided by T wall minus T infinity. Okay, this nu gets cancelled here, this X gets cancelled here, so you have a K and U infinity and alpha. So this alpha, if I cancel, then this gives a rho CP. Okay, rho CP below. So you actually get this multiplied by rho CP U infinity. Okay, so Q dot double prime divided by rho CP U infinity into T wall minus T infinity gives me Stanton number. Okay, so if I from this try to write the expression for Stanton number, then this T wall minus T infinity will go here. I'll multiply by rho, and this tau wall I'll write it as in terms of CF by 2, and then we will simplify this. Okay, so we'll write the same expression here. Q dot wall divided by tau wall CP is equal to T wall minus T infinity divided by Prandtl USL plus USL, U infinity minus USL. Right, that's the expression that you have. Now, what do? I bring this tau wall. So tau wall is equal to CF by 2 into rho U infinity square. Okay, so I'll write that rho U infinity square so Q dot double prime wall divided by rho CP U infinity into T wall minus T infinity would actually be equal to, so this T wall minus T infinity has come this side, the CP is already there. So I just have to multiply, write rho U infinity. So this tau wall Okay, so let me bring this tau wall here onto this side and write this as Cf by 2 into rho u infinity square. Okay, and then this rho I bring it down here, and one u infinity I bring it down here, so the other u infinity remains on this side. Okay, so this rho has come here from here, so I'll get a Cf by 2 in the numerator. So this one rho u infinity t wall minus t infinity I have brought here, so I'll have a u infinity here which will go down below, so you'll get Prandtl minus 1 into USL divided by u infinity plus 1. Okay, so this is the expression that I'll get. Now I'll need to write the expression for USL by u infinity. So this again I will use the expression for the sublayer. At edge of sublayer, we say u plus equal to y plus equal to 5. Okay, so normally we go from y plus equal to 0 to 5 as a sublayer. So u plus equal to y plus equal to 5 at the edge of the sublayer, and this is equal to u star u by u star, right? So this is basically at that location it is u is USL, so it is USL divided by u star. U star is nothing but square root of tau wall by rho. Okay, and the square root of tau wall by rho tau wall by rho u infinity square is Cf by 2. So square root of tau wall by rho u infinity square is this. So if I take the u infinity to the other side, it will be Cf by 2 into u infinity. So this is square root of Cf by 2 into u infinity, because tau wall by rho is Cf by 2 u infinity square root of that will be this. So this will be USL by u infinity to square root of Cf by 2. Okay, so therefore what we can write, USL therefore is equal to 5 times u infinity into square root of Cf by 2. Okay, so USL by u infinity can be written as 5 times square root of Cf by 2. So that I can substitute here. So I get the Stanton number, which is at any x, which is equal to q dot double prime wall divided by rho CPU infinity into t wall minus t infinity. Okay, so this is what we wrote in the last class. This becomes equal to Cf by 2 divided by 1 plus 5 square root of Cf by 2 into Prandtl minus 1. Okay, so this is the expression that you get. You recall in the integral method we had a very similar expression. Integral method, we had obtained STX equal to CFX by 2 divided by 0.9 plus square root of Cf by 2 multiplied by 13.2 PR minus 10.25. Right, so this is the expression that you got. So you compare with this. This 1 has become 0.9 here, but that's because we assumed the Prandtl number, turbulent Prandtl number to be 1. Actually, turbulent Prandtl number by experiments comes out to 0.9. The square root of Cf by 2 is there. You have a 5 PR minus 5 here. Instead, you have a 13.2 PR minus 10.25 in the experimental data. So that's the difference that you get. But this is from the integral method. This is also not the most accurate solution, but yeah, this is closest to it because these data are got from the experiment. So this and this, if you compare, this gives you a more approximate solution, but this did not involve as much algebra as we had done there. We just wrote two expressions, one for the sublayer here and one for the core here, and from those you could directly get, by eliminating that TSL, you were able to get the Stanton number, right? So this is your expression using the Prandtl two-layer model. It's a much simpler formulation. This was the first formulation that was done, and it has this limitation that you have considered the same sublayer for both momentum and the energy. That may not be strictly valid when your Prandtl numbers deviate substantially from unity, particularly on the lower side. It is found that for larger Prandtl numbers there is not a problem. Similarly, the approximation of y plus equal to 5, instead of this u plus y plus equal to 5, if you had taken a value where the u plus y plus the two-layer models, it's somewhere like 11.6, which we found in one of the earlier formulations. If we had done that, then this 5 would have become 11.6, and you would have gotten a value which is closer to this one. So that is basically that. So instead of 5, suppose I use 11.6 or 13.2. So basically the thermal boundary layer, they say 13.2, and momentum boundary layer, they say 11.6. So that is the deviation that you typically get, and the Prandtl number. Otherwise, this expression is quite similar to what we got from the integral method, right? So this is the two-layer approximation for the boundary layer flows. Okay, I hope that it's clear to understand. Now, what we will do is also understand the three-layer model by von Karman, because that's another classic model where you say that there is no sharp boundary between the sublayer and the core, but there is a buffer layer in which the two viscosities, the molecular and the turbulent viscosities, are of the similar order. Okay, so this is Karman's three-layer model for turbulent bond layer. So what do you say? You say that this is the wall. So you have a sublayer and you have something called a buffer layer. So in this one, alpha is much greater than alpha t and mu is much greater than mu t, and here you have mu much less than mu t and alpha much less than alpha t in the core region. This is the buffer layer, and this is the sublayer. And in the buffer layer, you say mu and mu t are of similar order, alpha and alpha t are of similar order, so they have to be kept and they cannot be neglected. And von Karman gave the limits of this as y plus equal to 5 and y plus equal to 30 as the limits. And he also gave a boundary layer velocity profile here, saying u plus is equal to minus 3.05 plus 5.0 log y plus. So this is a velocity profile which Karman gave, and these limits of the region. So we are going to use those three based on Karman's experimental observations, whatever he got, and the velocity profiles that he got. We will be using these in resolving the because you need to know something about the velocity profile in order to get the temperature profile and Stanton number, and therefore we will be using those approximations. So now suppose I start with the Karman's three-layer model, saying that okay, so you have u del t by del x plus v del t by del y is equal to del by del y of alpha plus alpha t del t by del y. Okay, and u del u by del x plus v del u by del y is equal to del by del y of nu plus nu t into del u by del y. Okay, so if you have these two as the equations, so we say that both in buffer layer and in the sublayer, u, v are negligible. Okay, so in both of them then I can write this expression, which is basically alpha plus alpha t multiplied by this is a constant and nu plus nu t multiplied by this is a constant. And if I consider both of these in the inner layer, then I can say this constant is equal to the wall flux by rho Cp here and the wall wall shear stress divided by rho here. So that is basically what we say. So in sublayer, we can say that alpha t is negligible. So alpha del t by del y is minus q dot double prime wall divided by rho Cp, and nu del u by del y, because nu t is negligible, is equal to tau wall by rho. Okay, so this is the expression that we write for the sublayer. As well as the buffer layer. So both of the both sublayer okay. In the sublayer, let me keep it first generic and then make it specific. So I'll write alpha plus alpha t and nu plus nu t. So in both sublayer as well as buffer layer, I say that these expressions are valid. So if I take this alpha plus alpha t to the other side and del t by del y is equal to this divided by this, and integrate over y value between the wall and any y value in the region of sublayer to buffer layer, then I will be able to write this one. So I write, if I just take this and integrate, taking this, so del t by del y is equal to minus 1 by alpha plus alpha t into q dot double prime wall divided by rho Cp. I integrate this from y is equal to 0 to any y in this region. Then this will also be integrated. Dy is equal to y is equal to 0 to any y in this region dy. Then what I get is this becomes actually t at y minus t wall. Okay, and so this will be integral. The q wall by rho Cp will actually come out, and because these are independent of y, we'll be able to write with a minus sign, of course, here 0 to y of dy divided by alpha plus alpha t. Now, what do? I write this in terms of y plus instead of y. So, what is y plus? Y plus is equal to y into u star by nu, which is y by nu square root of tau wall by rho, and tau wall by rho I should be able to take it out as of the integral. So dy is equal to or dy plus is equal to dy into square root of tau wall by rho divided by nu. So now I can write dy is equal to dy plus into nu by square root of tau wall by rho. So I'll be able to rewrite this expression in terms of that. So if I say t at y plus, and since there is a negative sign, I bring it here, I write t wall minus t at y plus is equal to q dot double prime wall divided by rho cp into square root of tau wall by rho multiplied by integral from 0 to y plus of there will be a nu that will also come. That nu will go inside there. So dy plus divided by alpha t by nu plus 1 by pr. Okay, so this is the expression that we get for y plus less than or equal to 30. Okay, because we are integrating this in the range between 0 to y plus 0 to from wall to the buffer layer. Okay, so now here in sublayer we can say that alpha t is much less than alpha, so alpha t by nu is much less than 1 by pr. So I can neglect this term. So the Prandtl number will go up and come out of the integral. So I can get t wall minus t at any y plus is equal to q dot double prime wall into Prandtl divided by rho cp into square root of tau wall by rho multiplied by, this will be just dy plus. So integrating from 0 to 5, so this will be y plus equal to 5. So if I integrate from 0 to 5 through the sublayer, then I'll get t at y plus equal to 5, which is actually TSL. Okay, and this integral will be y plus between 0 and 5, so it will be 5. Okay, so this is nothing but 5 q dot double prime wall pr divided by rho cp into square root of tau wall by rho. Okay, so this is the first expression that I get, the difference between t wall and TSL. I take this equation number 1. Now similarly, if I integrate it for the buffer layer, so I integrate this equation between the 5 to 30. Okay, so what do I get here? Then it will be TBL minus TSL. No, sorry, TSL minus TBL. Because that is like the T wall is a fixed quantity, so instead of 0 to y plus, if I go from 5 to 30, so this becomes at 5 it is TSL, and so it's TBL minus TSL. Okay, and this would be equal to q dot double prime wall divided by rho cp square root of tau wall by rho multiplied by integral from y plus equal to 5 to 30. And what do you get here? These two terms will be of similar order of magnitude, so neither can be actually neglected. So you will have dy plus divided by nu t by alpha t by nu plus 1 by PR. Okay, now this alpha t by nu I would like to get from the results that I know in fluid mechanics from the velocity profile expression that I have. So if I go from the momentum equation in the same way as I went for the energy equation, in the energy equation I wrote the Q is approximately equal to Q wall by rho Cp, right, in the entire region. In the same way I can use this tau wall by rho, U del U by del Y is tau wall by rho. So if I do that, then U plus nu t into del U by del Y is equal to tau wall by rho, right? And now what do I do? This tau wall by rho is okay. So if I write it in terms of in the left hand side, this side let it be. This actually is tau wall by rho is actually U star square. And what is this? This will be nu plus nu t multiplied by this. If I write in terms of del U plus by del Y plus, so U plus is equal to U divided by U star. So du plus is equal to du divided by U star. So I'll get a U star into du plus here. Similarly, Y plus is equal to Y U star by nu. So dy plus is equal to nu y by nu into dy by nu into U star. So du plus by dy plus, so du by dy which I have here will actually become du plus by dy plus with a U star squared by nu. So this into U star squared by nu into du plus by dy plus. Okay, so now if I cancel out the U star square from both of these sides, I will be able to get 1 plus nu t by nu into du plus by dy plus is equal to 1. Okay, now du plus by dy plus I can get from the von Karman's profile. U plus in the buffer layer, U plus is equal to minus 3.05 plus 5.0 Y plus. So if I differentiate this, I'll get a 5 divided by Y plus. So this is du plus by dy plus is 5 by Y plus. So if I write that, then if I take it to the other side, it will become Y plus by 5. So nu t by nu would actually be equal to Y plus by 5 minus 1. So that is the expression that I will get now. Nu t by nu is equal to Y plus by 5 minus 1. Okay, now since nu t is approximately equal to alpha t according to the turbulent boundary layer theory, turbulent Prandtl number is approximately 1. I can write this is also approximately equal to alpha t by nu. So I can substitute this for the alpha t by nu in this expression. So this expression where alpha t by nu is there, I'll be able to substitute y plus by 5 minus 1. So if I do that, then I get TBL minus TSL is equal to q dot double prime wall divided by rho Cp square root of tau wall by rho, and integral from y plus equal to 5 to 30 of dy plus divided by nu t by alpha is y plus by 5 minus 1, and plus you will have a 1 by PR. Okay, so now if I integrate this, I will have to take a common denominator. So the denominator will become y plus minus 5 plus 5 minus 5 PR plus 5 divided by 5 PR. Okay, so this 5 PR going to the top will actually make so this will be 5 PR dy plus divided by this whole thing. Okay, now if I have to integrate this, then since PR and 5 are constants, I can take the whole denominator as some z. So z, and what will be dz? Dz will be dy plus okay, so there is a PRY plus here into PR, right? Because if I take a common denominator 5 PR, this becomes a Prandtl Core. Okay, so if I take this as z, in the numerator the PR dy plus will be dz, so the 5 will actually come out, so it will be 5 times dz by z. And what will be the integration between y plus equal to 5 becomes, this will be 5 I substitute here, that will be 5 PR minus 5 PR plus 5, so 5 PR will get cancelled out, so the lower limit will be 5, the upper limit it will be 30 PR minus 5 PR, which will be 25 PR plus 5. That will be the limits. So if I can do the integration, this is log z, which will be log of this divided by this. So if I divide this by this 5, so it will be 5 PR plus 1. So you basically get this is equal to q dot double prime wall into 5 divided by rho Cp square root of tau wall by rho into log of 5 PR plus 1. Okay, so this is TBL minus TSL. Okay, so this I'll call it as equation number 2. We have got this equation number 1 for T wall minus TSL, which is again 5 Q wall PR by rho, so this one. So it's very similar to this, except that you have a log term here. Okay, so this is the second expression. Now the turbulent core, like we did in the Prandtl's model, we can do a similar thing here. Q dot any y divided by rho Cp is equal to alpha t del t by del y with a minus sign, and tau wall by rho at any location is equal to nu t into del u by del y. Right, so this is the expression that I can write for the shear stress and this one heat flux at any location. So I just divide these two and say that the heat flux and Q wall, the ratio of those, that's quite similar to the so if I divide these two, I get Q dot divided by not tau wall, it's actually tau. Okay, at any location. So now this will be Q divided by tau Cp is equal to minus dt by du, which is approximately equal to q dot wall divided by tau wall Cp. This is the Prandtl hypothesis. Okay, so we will basically just follow that and therefore integrate it in the same fashion as we did earlier between now buffer layer edge to the edge of the boundary layer, which is infinity. So we'll say T infinity minus TBL, okay, is equal to minus q dot wall by tau wall Cp integral. So this will be du is integrated, so it will be u infinity minus ubl. Okay, so this is the expression that you get. So this u, you take it to this side and integrate between the buffer layer edge and the free stream. So this is the expression that you get. Now you substitute for ubl from u plus y plus relationship. Okay, so let's go to the next page. T infinity minus TBL. Okay, there is a minus sign there, so I'll take that minus sign in here, so it will become TBL minus T infinity. Okay, so I'll then write without the minus sign q wall divided by tau wall Cp multiplied by u infinity minus ubl. Now if I write u plus equal to minus 3.05 plus 5.0 log 30 at y plus equal to 30. So this u plus is nothing but ubl divided by u star. And this, if you evaluate, this comes to around 14. Okay, so this ubl becomes 14 u star. So I can write it as 14 u star. Okay, so now if I want to write this expression in a fashion quite similar to the other two, q wall divided by this kind of expression. So this square tau wall by rho, I can take it further out. So this I can write as equal to divided by tau wall by rho into rho Cp. Okay, and in this expression you have a square root of tau wall by rho, so you have you keep one square root of tau wall by rho, the other you take it to the other side, multiplied by u infinity minus 14 u star. Okay, so now tau wall by rho is or square root of tau wall by rho is u star, right? So this is one square root of tau wall by rho I can keep here. So I'll write it as square root of tau wall by rho into square root of tau wall by rho. This I can take it as u star and take it this side. So this will become q dot wall divided by rho Cp square root of tau wall by rho, which is quite similar to that, multiplied by this will become u infinity by u star minus 14. Right, so now this expression has become quite similar to that. So now I have an equation. This is what is this? This is equal to TBL minus T infinity. So this is an equation which I call it as equation number 3. So if I add these three equations, equation number 1 is Twall minus TSL, and equation number 2 is TBL minus TSL. And so, okay, TBL minus TSL should have come with a negative sign, so it should have become TSL minus TBL, right? So there is a negative sign here, which should have gotten absorbed here, right? So TSL minus TBL, and finally you have a T infinity, TBL minus T infinity. So if I add all of these, I'll get a Twall minus T infinity. Okay, so 1 plus 2 plus 3 gives me Twall minus T infinity is equal to, I'll have this as common, Q dot double prime wall divided by rho Cp square root of tau wall by rho is common in all of them. In the first one I have a 5 PR, and in the second one I have log of 5 PR minus 1. Is it minus 1 or plus 1? 5 PR plus 1. And in the third one I have U infinity by U star minus 14. Okay, now this I have to simplify. So what I'll do, I'll take this as square root of tau wall by rho. Tau wall by rho is Cf by 2 U infinity square, right? So if I take square root here, I'll take a square root here. This will also become square root. So I'll have square root of tau wall by rho is equal to Cf by 2 into U infinity. So I'll keep the U infinity here and take the Cf by 2 into that. So this will actually become equal to Q dot double prime wall divided by rho Cp U infinity multiplied by, this is square root of Cf by 2 going inside. So 5 PR plus log of 5 PR plus 1 plus this U infinity by U star. What is this? Now U star is square root of tau wall by rho. So U star by U infinity will be square root of tau wall by rho U infinity square, which is Cf by 2 square root. So U infinity by U star is 1 by square root of Cf by 2. Okay, minus 14, whole thing divided by square root of Cf by 2. Okay, so now I can get an expression for Stanton number quite easily, because that will be Stx is equal to Qr divided by rho Cp U infinity into Twall minus T infinity. Okay, so this Twall minus T infinity coming down here and this going to the other side will become square root of Cf by 2, and if I take a common denominator here into square root of Cf by 2 will come again, this whole thing divided by, okay, what will happen, this will be 1 plus square root of Cf by 2 multiplied by 5 PR plus log of 5 PR plus 1 minus 14. Okay, so this is the expression that you get. Okay, I'll write this again on the other page. This is Cf by 2, because square root into square root is Cf by 2 divided by this. This is again, you can see the form is quite similar to what we had seen earlier. So let me just write Stx is equal to Cf by 2 divided by 1 plus square root of Cf by 2 into 5 PR plus log of 5 PR plus 1 minus 14. Okay, again you can compare it with the earlier expression. Integral method, you got Stx is equal to Cf by 2 divided by 0.9 plus square root of CF by 2 into 13.2 PR minus 10.25 is one expression that you had. And in the other expression that you had for Prandtl number, Prandtl mixing length or Prandtl two-layer model, you get STX is equal to CF by 2 divided by 1 plus square root of CF by 2 into 5 times PR minus 1. Okay, so this is one expression, this is the other expression, this is the third expression you've got. So they're all quite similar to each other, and you find that you are able to get these expressions of the Prandtls and Karmans much more simply than the integral method. Integral method involved a little bit more complexity, but even this is a simplified method. But complete theoretical solution to get the turbulent boundary layer profile requires direct numerical simulation, so we have not done that, but mostly the data from experiments is used to verify this. Okay, so that brings us to the close of the discussion that I wanted to have on the simplified, more classical methods of the turbulent boundary layer profiles. And we find that the discussion that we have had so far shows that by multiple methods we arrive at quite similar expressions depending on the extent of approximations involved. But if we can numerically calculate this, which I'll give it to you as a homework to do, if you can numerically calculate this, you can get the skin friction and Stanton number from all of these methods in a rather simplified form and see how approximate that is with respect to the measured or correct values. Okay. In the next class, I will conclude this by discussing the significance of local versus averaged heat flux as well as shear stress, and therefore local as well as averaged result number and the skin friction coefficient. Okay. So we'll discuss that, and particularly when there is a transition from laminar to turbulent in the boundary layer, how to take that into account is something that we will do. And we will also use, we'll also present some of the most commonly used turbulent flat plate boundary layer correlations for different ranges of Prandtl number. Okay, so we'll then stop with that for the boundary layers and then move on to internal flows. We'll stop here at this point for this lecture. Thank you.